What if we deny? Will you not take class? Wow, these dictators are like too much, yeah? No, I will still take the class. Okay. All right. So today we're going to be talking about something very exciting. Um, First off, before we start, can somebody help me pronounce this title because I have no clue how to pronounce it. Uh, I don't know. Like,
Spelling must be wrong somewhere because it is a red.
no, it's German. It's supposed to be German, so that's why it's red. Um,
Let's just call it ease problem. Ease.
uh, wow, you came up before you started trying. I like that attitude. Like, is there somebody here who knows German who can like help us pronounce this because this has been like a problem I haven't solved for quite a while. Entscheidungsproblem. Problem. I don't know.
I think the EI is like shy. I'm
Okay,
not
so
sure.
what does that become?
Entscheidungsproblem.
That
Possibly.
sounds right. That sounds right. That sounds right. Okay, we'll take Shreya's word for. I have already forgotten the pronunciation, but anyways, so this is I want to start with a story. So in the 20th century, there was a famous mathematician called David Hilbert. Have you guys heard of him? David Hilbert is apparently not that popular. Yes, from Hilbert Hotel. Yes, that's the Hilbert guy. It's true. So that guy, he has a bunch of things. So David Hilbert proposed this list of I think 21 or 23, I forget, problems which he thought were important for mathematics and humanity. Like if we solved them, then we would be making huge progress in math and CS as you know it. He is popular. Okay. Trump Trump says he is popular, so surely he must be. Okay, anyways. So one of the problems was this on soy whatever problem. And the problem stated something like in very loose terms, is there a mechanical procedure to solve every problem? So what does this even mean, first of all? This is quite very loose. But what Hilbert was trying to get at is given any problem, if we have enough time and enough resources in the world, then can we like due to by some mechanical procedure or by some way or the other, can we eventually like solve it? Like basically that was what his question was. And of course, like at that time Hilbert thought the answer was yes. Because surely like every problem you have, surely eventually it has to be solvable, right? Like maybe it takes you 1,000 years, maybe it takes you 10,000, maybe it takes you 10 million years, but surely every problem you can eventually solve. Uh, so this is the problem that we are going to try and understand and hopefully also solve by the end of today, right? But before we even try, okay, are there any questions or comments on just this one so far? Okay. Okay, I have a question. What do you even mean by a mechanical procedure? What is a mechanical procedure? How do you formally or mathematically define what a mechanical procedure is? If you're putting something in the chat, I will probably not be able to follow the chat. So please unmute and uh,
Probably it's could something be done using computers, writing algorithms and stuff.
fair enough. So something that can be done using computers,
We
except
must
during
have a
Hilbert's time.
fixed series of
Yeah.
steps which will solve every problem.
Okay.
An algorithm.
Okay. So fixed series of steps. I don't think Hilbert necessarily meant that the same series of steps should apply for every single problem. But maybe for every problem, there should be something where you should eventually be able to solve, right? That's what that's what the idea was. So okay. Okay, except like for this, I like this idea, except computers didn't exist back when Hilbert proposed this problem. Um But yeah, right now that's what he'll be loosely thinking of. But also what we want to do is we want to mathematize this as much as possible. So how can we define a mechanical procedure in terms of just functions and sets and things like that? So that's what we'll be trying to do today. Any other comments about what you think a mechanical procedure could possibly mean? Okay, we can keep thinking about it. We can come back to it. Um, Also to simplify over here, when I say a problem also I'm going to simplify it a little bit, and I'm going to say that okay, um, just so that my definition of a problem is like nicer, I'm going to define a problem this way. So, uh, you're going to have a fixed set of things. Let's say for now, you have your entire everything you can represent in terms of zeros and ones. So let's say you're only going to use, let's say, zeros and ones to represent everything for now, just to simplify things. And let's say so and let's say you have some fixed set that you know, for example, everything that starts with a zero, right? Maybe this is one side. So this is all the things that start with a zero. Okay, obviously I can't write them. So everything, all that starts with a zero. So my claim is that any problem you have you can sort of think about it as defining some set which you want, which you desire, and then asking whether, for example, so does uh 0 0 1 1 0 0 belong to this set? So maybe okay, this sounds pretty out of nowhere, but I'll try to build up some more intuition for this. So let's say you want to know some fixed mechanical procedure by which you want to determine if something is a prime or not, say. So your set will be basically all the one way to define your set could be everything, all the primes in binary. And then whatever number you want to know whether it's a prime or not, you can just ask whether that belongs to the set of primes or not. So for example, 2, 3, 5, so do you write 7, 4 and 3, 7, so on.
So this doesn't talk about optimality or stuff.
Okay, that's a great question. So these kinds of questions are called decision problems, meaning you're only interested in yes or no questions. So my claim is that you can convert optimization. So who asked this question? Sorry, I missed it.
Lavish.
Lavish. So you can convert any convert any optimization problem into a decision problem. Let's say you want to optimize. So what do I mean by an optimization problem? For example, minimize this or maximize this, something like that. So if you want to, let's say, find the smallest number such that blah 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 happens, then what instead you can do is convert it to a decision problem and ask ki, is there an instance for less than k, where you can keep giving k for different things, and then you can keep reducing k until the answer turns to no, and then that's how you can find the minimum. That's sort of the idea.
Okay.
So mostly we'll just be focusing on decision problems for now, because optimization problems are sort of similar. You can convert any optimization problem into a decision problem as well. Okay. So yes, so that's how I'm going to define a problem. Just to make it somewhat more mathematical, you know. So now I can just in terms of sets and whether things belong to a set or don't belong to a set. That's a very easy, or like a simple way of defining what I mean by a problem. So I'm open to any of the definitions you might have as well for these things, but this is what we'll be using throughout the class for today. So this is what I mean by a problem. This is fine. Any questions or any comments or anything so far? Okay, if you have anything, just feel free to unmute and speak up. Okay, all right. So again, so now that we have some nice thing, let's try to look at some very easy model uh which could possibly simulate a mechanical procedure. So let's say you have some. So what you want to do is you want to have some sort of a system that tells you what to do for different inputs, right? Like for example, over here, if you had 0 0 1 0 0, you would want to do something else. Whereas if you had 1 0 0 1 1 1, you would probably want to do something else for us to understand whether this belongs to the set or not, whether this doesn't belong to the set. So the way we'll be doing that is in a very simple, the most simplest. Let me introduce to you, say hi everybody, to the most simple model of computation. I'll just name it later. So for now, we are going to have a bunch of circles. Hello, circles. And some of them will have arrows coming towards them. I'll explain everything later in a while. Some of them will be like this. And now what you're going to do is, what this means is that so these circles are, the formal word for them is a state. This means that it's a starting state, which means that's where you start. And once you start, then you should know where to go. For example, let's say if I read in a 0, I go here. So that's how I'll denote it. Whereas if I read in a 1, I should go here. That's how I'll denote that. And let's say I read in a 0 when I'm over here. So let's say I go here. Let's say I read in a 0 when I'm here. So I'll do this, for example. And let's say maybe I read in a 0 when I'm here. I should know where to go. Let's say I read in a 1 when I'm here. I should know where to go. Let's try to make this, sorry, this we have already done. This should be for 1.
On
And
what basis are we naming these 1 and 0? I couldn't get like how do
right,
we
so what we
decide?
want to do is, yeah, let me just copy paste the DFA I already have from material. Let's just quickly make something that makes sense. So for example, let's say you start here, and I tell you that if you read a 0, you should go here, and if you read in another 0, you should go here, and if you read in a 0 or a 1, you should just stay here, and if you read in a 1, you should go here, and if you read in another 1, you should go here, and if you read in a 0 or a 1, you should stay here. And from, or let's do something like this, 1, and you read in a
There's a
0.
question in chat about optimization. So, when you converted the
Okay.
optimization problem to the decision problem, it may take infinitely many choices of k to get the right answer. Meaning you can only solve it in infinite time, but we only get finite amount of time.
Oh, okay. You can optimize that also, meaning you know that, if you know that the answer is going to be finite, then you can multiply by 2 each time and sort of binary search it out or something like that. So if you know that your optimization is going to be finite, then you shouldn't need infinitely many. Also, like for now, just to simplify things, assume everything is an integer or something. Like let's not get into the optimization thing. But that's a great question though. Mm, yeah, this is much better. Okay, so let me explain what I mean by all this jargon, circles, and this thing, so 0 and 1. What this means is basically anything at the start of anything, you start at the start. You start the start, and these concentric circles are called final states or accepting states. Okay, so now let's say you read in something like 0, 0, 1, 1, 0. Then you would, since you started the start state, then you would go 0. Then, oh wait, my bad. This should only have a 1 here, and this should also only have a 0. Yeah, and then you read in another 0, so you go here. Then you read in a 1, so you know you should go here. Then you read in, okay, another 1, so you go here, and then you read in a 0, so you go here. And then you end at something which is not 2 circles in a row, right? So that means that you don't accept the string, so you reject the string. Instead, if you had something just like 0, 1, 0, 1, or 1, 1, 0, 1, say, then you would start here, you would go here, 1, 1, 0, 1, and you would end at an accepting state, which means you would indeed accept 1, 1, 0, 1. Is this fine? So that's how we are going to deal with these things. And the basic rules are that if you are at any state, you should know for sure where to go no matter what input you get. For example, you can't, for every state basically means should have 2 outgoing arrows. One should tell you where to go if you see a 0, one should tell you where to go if you see a 1. And of course, since you only want finite computation, you only want finite number of states. That's all the rules. So you'll have one starting state, a bunch of final states. You can have more than one, two, like over here. You should have 2 arrows coming out of every state, which tell you where to go. And that's what you do. That's basically going to be your automaton. Okay, now I hear people complaining. They're like, okay. First of all, before I talk about why I'm hearing people complain, um, is this fine? Like, does this make some sense as to what we're doing with these circles and arrows and starts and finals?
Can I get to know why the first one was wrong?
Okay. Even this one is kind of wrong. I'm sorry. Like, it was not wrong. It's fine. I was just trying to create something meaningful out of it. This is also fine. It was not wrong in any way. I was just trying to create
What
something
meaning
meaningful.
does it give? Like,
Even
what does
here
it?
I've failed, but surely we can cook some meaning for this, yeah.
I mean,
What is what I mean by meaning is like, can you describe exactly what sort of strings this accepts?
okay, okay.
This is very badly made, so I think we'll probably have to like cook for some time to see what sort of things it accepts. But we'll cook something better. We'll cook something better together.
I
So
think we
don't
can
worry about
characterize
that.
like all strings, like if you pretty much because like it's finite.
Yeah, that's
Like
a great intuition. Yeah.
so like in the first like the two circles, like the top one, like the top half of the two circles,
Yeah.
like to get to that, like you need like 0 and then some
Hmm.
any number of ones, and then you'll have
Yeah.
0 and then you can alternate between 1 and 0 sufficiently till you reach a 0 if you are going to end in the
Hmm.
first state. So you can characterize strings like that for this.
Interesting. Yeah. So you can actually like create some sort of meaning for this, as Nishant said. So it is quite scuffly made. We'll come back to this. I'll just give this as homework for okay, characterize this. So because I don't want to spend time in class doing that. But is it first of all fine how these things are working? How this works and what to do if you see some string and stuff. Is this
Yeah.
fine? Is okay, any questions? Uh, just please feel free to ask if there's any questions about the workings of this. Okay. Um, yeah, I think that's enough of a pause to ask questions. Okay. Now, yeah, I already hear people complaining. They're like, okay, but this is like all still in the air. Like, where's the math part? Like, how are you still doing this mathematically? So now bear with me for like some 2-3 minutes because now I'll show you how I can make this more mathematical and define this just in terms of sets and functions. So what I'm going to say is in fact for any, so this has a name. It's called, does anybody know what it's called? It's called a deterministic finite automata. And this deterministic basically comes from the fact that you should know for sure where you're supposed to go if you're at any state. Finite because it's finite, and automata because it's an automata. Very great naming. I like. I approve. Okay. All right. And the way you define it, okay, first of all, you need a bunch of states. I'm going to say Q. I'm going to define Q as my set of states. So this is going to be set of states. Out of which, let's say one of them, I want them to be my starting state. So this is going to be my start state. Then I also want a bunch of ending states or accepting states. So Q belongs to the Q, by the way. F is going to be some subset of Q, which denotes the finished states. Okay. Then I'm going to have something called an alphabet. For example, my alphabet here was only 0 and 1, meaning any string that I take consists only of 0 and 1. But I don't have to stay restricted to that. So I can have anything. Like I can have 0, 1, 2, I can have ABC, I can have anything. So anything I want. So I have an alphabet. So over here it's just 0, 1. Okay, so that's that. And now for the most important part, I need to have a transition function, right? What does that mean? That means that I should know where to go if I'm at what state and how it works. So I'm going to call that function delta. So the delta is a function. It's going to take a state as an input and an alphabet and a letter as an input, and it's going to output another state. So what does that mean? It means it's all it's saying is it tells me if I'm at this state and I get 1 as input, then where should I go? So let's call these states something A, B, C, D, E, F. So over here, this would just mean that delta of B comma 0 is C, or delta of B comma 1 is B. What is delta of D comma 1, for example?
Where is D?
Just as a quick, D is over here.
Okay, it's E then.
Yeah, exactly. Does it make sense what delta is? Yeah, so we have this transition function delta that we have. So yeah, I think this is all we need to define a DFA, right? We need some finite set of states, we need some way to go between them. That's all. So this is how you would mathematically define. So don't worry, this is just for me to like convince to you that okay, what we are doing is like it's not all in the air. You can write it out like this and you can do rigorous stuff. In fact, we will be doing some rigorous stuff with it.
Oh,
Yeah.
wait, so in each state, we have only a fixed number of outcomes. That means there's no outcome outside of that. Is that
Yes,
right?
yes. Since it's deterministic, for any input of strings, you should know what there should be one state you should end up at. Like at no point should you be confused as to I don't know where to go from here now.
Okay, got it.
Yeah. Okay. Okay, let's try to cook some nice DFAs. Like for example, can you help me make a DFA which only accepts strings that are, let's say, end with 0? What that would mean is can we answer this question? Is a number even? When is a number even? When it ends in a 0, right? So can DFAs recognize whether a number is even or not? So i.e. does string end with 0? So now your language end with 0. So language, just going to use the word language for the set that a desired set, or so usually L is going to be a subset of 2 to the sigma. What that means is you just have some subset of all possible strings that you can form. So over here, the strings that we want to accept are precisely these. Blah 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 blah, ending with 0. So can we make a DFA that accepts strings which only end with zeros? Meaning that if you give a string which ends in a 0, it should end up in a accepting or final state. And if you instead give a string which ends in a 1, then it should end up at a rejecting state. So can we make a DFA like that?
Like we can have just 3 states, one ending, one starting, and one the intermediate. And we can just
Okay.
cycle the intermediate whenever it is 1, and if it is 0, if it ends with 0. Like,
Right. Okay. So let's say I see a 0 at A, then I should just go to C. If I see a 1, I will go to B. If I see a 1, I will go here. If I see a 0, I will go here. If I see a 0, I'll stay here. If I see a 1, I will go here.
yeah, something like this.
It is A even required? Like, can't you just take out A and then like plug everything in and then add a 0 at the start of every string?
That's a great question. Can you? So first of all, even before we go to that, let's make sure. Are there any questions? So let's take a few examples just to make sure that everybody's on the same page. For example, what happens if you read in a 1 1 1 0 1 0? So you'll first go 1, then you'll go 1, then you'll go 1 again, then you'll go 0, and you'll go 1, and a 0. And you reach an accepting state. So nice, you have accepted it. And let's say this last 0 wasn't there, so you would have just ended up 1 1 1 0 1. You would have ended up here rejecting the string. In fact, what you're doing over here, the idea is that every time you see a 1, just go to this state, which is not accepting. But the moment you see a 0, just go to the accepting state. Okay. Is this idea fine? Does this make sense? Okay, I'm just going to take random names and ask people if this is fine, and people should. Uh, okay, I have like there's some great questions in the chat. So either if you're asking in the chat, put them in the everyone chat. Don't DM me because I don't follow the DMs. Right now, I am just reading them out though. Or just unmute and ask. I would actually encourage you to just unmute and ask because the class has been very quiet and it's been me yapping for way too long. Why do we have to check all digits instead of checking the last digit? Okay, that's a great question. Does somebody else want to answer that?
Because we'll
Why
have
are
to
we?
know
Yeah.
we'll have to
Yeah.
know when the string finishes, and for that you need some way to check the length of the string of zeros and ones.
We cannot go directly to the end of the string without checking.
Yeah. And that's right. So it's not like us doing the computation. Or also like imagine you have like an incredibly huge string with like a million digits. And the only way you're allowed to look at the string is like from the left, right? That's how you read numbers. Like you then you'll have to, that's how you'll have to do it. That's basically the idea that you can't directly go to the last digit simply because it's the last digit. So you have to go through everything before you get access. And also it's the computer doing it. So how does the computer or this automaton or this mathematical model that we have, how does it know that this is the last digit? So it doesn't directly get access. The way it gets access is if you have to go sequentially, just simply because it's the last digit. Does that make sense? Why can't we just mod 10? What do you mean? Uh, till oh yeah, till the time the person in the chat asks the question again. Yes, we'll come back to Nishant's point. Nishant is saying, why do we need 3 states? Surely we can do better. Right, Nishant?
Yes, I thought so.
Yes. thought so, and now he's probably not so sure anymore. Can you do it in just 2 states though?
You can add a 0 to all strings. Like that is clearly allowed.
So
And then you make
no,
your
what do you
entry
mean?
state. Like I can add a 0 to any string, right? Like it doesn't might change anything. If I add a 0 in the start, like the number keeps its value. Technically.
Oh, you can't change the input in any way if you're saying that. So your input is just going to be like you could have, and you still want to be able to cope with 1 as the first digit as input if you that's what you're asking.
Yeah, so but I can just start at 0, whether or not the input is like I just accept like take my initial state to be 0, and then if it's 1, I can
Hmm.
just shift back to the 1. Like I don't even need A at this point. Like I can just start at the state I want.
So you're saying that there should only be one state and that should be the final state?
No, there should be 2 states, like 1 for 0 and 1 for 1,
Okay.
and there should be no input
Okay.
state.
There should be no input state.
Like we
No,
have
that's not
A.
allowed. You have to have you need to know where to start.
You can just assign it to be starting at A, right? Because like once you start at A,
Okay.
you look at the first thing, and then it's
Yeah.
0, so you just stay there. And if it's 1, you go to B.
I see. So you want A
Oh
to
wait,
be
I
the
mean reverse. It's
accepting
reverse.
state.
Yeah,
Yeah,
reverse.
yeah.
Okay. Okay, so if it's 0, you go here, and if it's 1, you go here. And what do you do at B if you see a 0 or if you see
If
a
it's a
1?
B, you'll see a 0, like go back to itself, and you see a 1, you go to A.
Yeah, exactly.
So like we've done only 2 states.
That's great. Yes, this works. It's quite neat. Does this make sense? Any questions?
Yeah, it does.
Okay. Okay, I'll give it like another 15 seconds for people to ask questions or make comments or anything like that. Okay. All right, nice. What if we want to do something, what is like, give me some other language now. Let's try to see. So what do you think? Do you think like given any set, so now I do have like, okay, you guys don't have any questions, but I have a bunch of questions. First of all, can we make DFAs for anything we want? What do I mean by that? What I basically mean is uh given any set given any set L, given any subset L of strings, can you always construct a DFA which recognizes precisely these strings? What I mean by that, it should only accept these strings and reject everything else. That's what I mean by DFA recognizing a language.
What if like there is no pattern between them? Like in primes, there is no pattern between primes.
We've not discovered a pattern. We don't know if there is.
Like
Okay, what
like
is
in the
something you think we can do? What is something you think we can surely do?
Wait, we're supposed to recognize strings, or what was the question again?
Yeah, the question is what sort of languages can we construct DFAs for? Like for example, let's take another example. Can you say keep track of whether the first and the last character of the string are the same? Or let's say going one step further, can you accept only palindromes and reject everything else? Or how about something like accept words only which are like 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. Which one of those seems most interesting? We can take one of those up and try to make a DFA for that. Or how about something with only an even number of zeros? Or how about something that ends with like 0, 0, 0, 1, 1, 1? Only accept those. I don't know. I'm just saying out random things. Is there anything that you want to particularly do that you think would be interesting to do on a DFA? You could.
palindrome one seems interesting.
Okay. So how would we keep track of whether something's a palindrome or not?
Can you have multiple DFAs running simultaneously? Or like only one
Can
is
you
running?
have what?
Multiple DFAs running simultaneously. So at the end, we check if each DFA reaches a particular state, and then like,
Ah, I see. So you're saying that you have multiple DFAs
yes.
as long, and then each DFA reaches some particular state, and then what do you do?
And then I
Like,
like decide, and then looking upon all the possible reachable states, I create a new DFA, and then it decides key what the end state is.
I don't get it. So what are you trying to do?
Well, I want to see all of these DFAs will reach an end state, right? So like
Yes.
for each possible reachable end state, it will be some number, like it's finite for obvious reasons.
Hmm.
So like we can create a new DFA which like takes in the input as the ends, like the like set of end states of these DFAs. We can create a
Okay.
new one. And
Okay.
then we can figure out key what is our actual end state.
Okay, so you want, based on some combination of these end states, you want to again do some sort of computation to determine if you would want to accept or reject.
Yes.
Okay, my question to you is, can you combine this and just like instead of simulate this using just one DFA instead of having multiple DFAs? And what is like the motivation to think about this even? Why would you want to do something like this?
I mean, in palindrome, you want to check the first and the last, right? So you want to
Hmm.
like try getting like as much info, like you want to get two pieces of information at once, like at the end.
Okay, so,
Right.
so let's start simple. So let's make a DFA where you accept only if the first and the last characters are equal, right? Let's start with some start state. So let's say first and last are equal. That's what you want. So how would you do that? Just tell me, I'll add a bunch of states randomly. Tell me where to go, what to do. So let's say you see a 0, you go to B. Let's say you, yeah, tell me what to do. Say it out.
Wait, we're doing it on a binary string or?
Yeah, binary string. Everything is binary for now.
Okay, if you see a 0, you go to B.
How are we like supposed to match stuff? Like if that is equals to that.
That's a great question. Can you even do that on a DFA?
I think if we separate, like if we see a 0, then you go from A to B. If we see a 1, then you go from A to C. And then we can sort of like separate it into two different cases. And then from B, if we see a 0, then we go to D. If we see a 1, we go to B. And just sort of make it the opposite on the other, on C. Would that work?
Okay, first of all, that's a good idea, but except this is not a DFA at all. Because if you're at D, you don't know where to go if you see a 0 or a 1.
Oh yeah, I meant and then 0 from D. If you see a 0, you go to D. And from D, if you see a 1, you go to B. So that I so and the opposite on E. And D and D are the final states.
We can have two final states.
Yeah, in the first one, we did have two final states, right? You can have multiple final states, that's fine.
Oh, yes, we don't. Mm.
Does this work?
Yes, I think, yeah, it does.
Yeah, it does seem to.
Another interesting question to think about is whether this is the minimum number of states you would need to make this work. Can you do it in a lesser number of states?
We can just remove that starting state and can there be two starting states and stuff?
No, the idea behind having only one starting state is like you should know for sure where to start. Like if you have two starting states, how do you know where you would start? Also, I think there's a lot of nice intuitive ways to think about this. For example, B is a state where you go to if you're starting at 0 and ending at 1, right? C is a state that's keeping track of if you start at 1 and end at 0. And E is a state that's keeping track of if you start at 1, are you ending at 1? And D is a state that's keeping track of if you start at 0, are you ending at 0. That's the intuitive way to think about it. So in
So
fact, if
all
you
four.
wanted a yeah,
So we are keeping track of all four possible combinations and then plugging them along.
exactly. In fact, if you wanted a DFA which accepts only strings which start and end with a different character, then you just do this, right? So now my question is, now can you think about whether we can do better in terms of states here? For example, can it happen that let's say something starting with a 0 and ending with a 1, after you do a bunch of things, it reaches some state. Okay. Let's see you're somehow only able to do things with 3 of these states instead of 4 here, right? Let's assume for the sake of contradiction that you can do it with 3 states. And also notice here that you were keeping track of 4 different things. You were starting at 0, ending at 1, starting at 1, ending at 0, starting at 0, ending at 0, starting at 1, ending at 1. Now my question to you guys is, okay, can it happen that 2 of these fall into the same state? Or do we need sort of 4 states to separate them or distinguish them? Like let's say I have some other DFA which also recognizes the same language. And eventually what happens is, let's say there is some string which starts with a 0, ends with a 1. I reach this state. There is some other string which starts with a 1 and ends with a 0. Can I reach the same state? Can it happen? Like, is it possible that I reach the same state for both of these? So let's say after I read in a 0 from here. Yeah, Lavish, go ahead.
Like we won't be able to make sure in both the cases. Like if for the first case we'll need to just recycle it with 1, and if that happens then we are, for the second case we are just stuck there only. We won't be able to move.
Yeah, that's sort of the idea. The idea is that let's see if you read in a 1 from this point, and let's see you read some state, and then that's you end there. That would mean you're appending a 1 here and you're appending a 1 here. Then you would want to accept this string, right? But you would want to reject this. So you cannot possibly have both of these reaching the same state. Because after reading a 1, one string you must accept and one string you must reject. So these two strings, you sort of want to keep them as separate as possible. You never want to keep them in the same state because it creates this sort of a problem. Does that make sense?
Yeah, similarly we can do when both of these cases are same, ending with same and same, and we can append one and the same logic works.
Yeah, exactly. If you have like something like 0, 0 and 1, 0, then again also you want to distinguish them. We don't want to keep them same. We want to keep them separate because you can append a 1 and then it wouldn't make sense because 1 you want to reject, 1 you want to accept.
Yeah, but like 0, 0 and 1, 0 already fails, right? If this must be a final state, and then 1, 0 is obviously not an acceptable number.
Yeah, exactly. I mean, that's what. So if two people are in the same state, what does that mean? Like, let's say if two different strings end at the same state, what does that mean? Like, let's call the two strings something. Let's call them A and B. Like, after I read A, I reach here. After I read B, I reach here. It means that if I read whatever I read after that, like if I consider something like A0 and B0, either both are accepted or both are rejected. I cannot have one accepted and one rejected, right? Does that make sense?
What if it's something like 0 to 1 and 0 to 0? Both of these are for the same state. Then
0 to 1 and 0, 0 to 0. Yeah.
appending 1 or 0 won't make any difference. If we append 1, then they are different and we can reject it. If it appends 0, then we can accept it.
True. So starting with 0, ending with 1, you could possibly make them in the same state. Oh, but that creates an issue because these itself are not the same, right? These themselves, this one you want to reject and this one you want to accept. So you don't want them ending at the same.
Oh, yeah, yeah.
So can we now write this more mathematically? Like when can two strings end at the same state? When can two strings A and B end at the same state? So first is of course when either both accepted or both rejected, right?
Yeah.
And further you also need this, but just this much is not enough. You need something stronger. Because, for example, consider 0, 0, 1, 1. Both of these are accepted. But you cannot put them in the same state. Why can you not put them in the same state?
Again, that appending stuff.
Yeah, so how would you write this? I can say that instead I can in fact make this more stronger. Maybe like there's some universe, let's say 0, 0 is still accepted. But if you append like some complicated string, the same complicated strings to both of them, one of them is accepted and one of them is
Just add
rejected.
1, right? Just add 1 to both.
Yeah, like for now we can see that in this example it works. But maybe like can it happen that let's say I append AS, some string S to A and B, AS and BS. Can can it happen that AS is accepted but BS is rejected?
No, because like they are the same state.
Yeah.
So they'll
Yeah,
have the same
because
exit, but like you
yeah.
want their exits to be different. So that's not possible.
Yeah, so AS and for all strings S, so for all S, AS and BS are both accepted or both rejected, right? Does this make sense?
Yeah.
Yeah. Okay. Let's try that let's try the palindrome question again, yeah? So now can you make a DFA for a palindrome? So you need a stronger DFA now. Before we go to that, are there any questions about this part? This is quite important and neat also. Okay. All right. Let's try to make a DFA for a palindrome. What's the idea? So what two strings can end at the same state now? Can you give me two strings that can end at the same state?
What is our letters or alphabet first?
0 and 1. Yeah, that's all. It's going to be 0 and 1 throughout. Okay, give me some two strings which can end at the same state. Or you know for sure that cannot end at the same state. Any information is useful information.
1 1
For
1
example,
1 1 0 1, for example.
sorry, what are your two strings?
1 1 1 and 1 0 1 will end at the same state.
No, but you can append
Okay.
something such that it ends at different states.
So what is that string that you're appending to give a counter example?
You can append like 101. Yeah, that should work.
Yeah, so if you append 101 to both of them, you want to accept this one, but you want to reject this one, right?
Yeah, I can
So
be.
111 and 101 must end at different states.
In fact, any two palindromes must end at different states. Any two distinct like palindromes.
Why is that?
Because like we can append some string s such that it fits. Like you can just append the other, like say A and B are distinct, then just append B to B and B to A, and then it fails because A is not equal to B.
Yeah. So any two distinct palindromes AB must end at different states, because if you consider A and BA, you want to accept this. And
What
how
if
can
the
you be sure
lengths
that
are
you want
different?
to reject?
Like, what if the lengths are not same?
Yeah. What if their lengths are not the same?
Sorry, I didn't understand. Lengths are not. What do you mean by lengths are not the same?
Like in the case above, they were both 3 lengths, so appending the string to itself worked. But what if it is like something 3 lengths and something 2 lengths?
And then we can do something similar. Like we get the picking of the string like uh how mathematically like just like we can just how do you say yeah, just mirror it,
Yeah,
right?
so is it like obvious why BA is always not going to be a palindrome?
I
If
mean,
B and A have different lengths.
wait, A and B are palindromes, right? We are assuming that.
Yeah.
Then yeah, B, A being a palindrome would imply okay, if they are different lengths.
Like for example, if one is 1001 and 100, then like you're saying mirroring it, it won't work this time. Mirroring this small one at least.
1001 and
100.
100 is not a
So you have
palindrome.
yeah, that's not a palindrome. You want both the things to be palindromes.
Yes, okay.
I mean, if we reverse BA, we'll get AB, right?
Yeah.
And that's not going to be equal since
Wait, it's not going to be. Oh, yeah, true. It is going to be AB because A and B are both palindromes.
and since A is not equal to B,
No, but they're
they
of
won't
different
be
lengths.
equal.
Stuff gets carved, yes.
Yeah, like then what we would want is like A is like a substring of B, but also the endings of A and B have to be the same. Does that work somehow? Like if you have 1001 and 1001 001. Yeah, it still shouldn't work, but we'll have to work a little more on the proof.
So we just need to construct the string S, right? Which doesn't work.
Yes. We just need to construct, maybe is there some other way we can construct something more obvious that doesn't work at all? That we know always. Or maybe we can also change up A and B a little bit. I think this should also just work, but we'll need some more work to show that it works. Um,
Hmm. Something I found works if we mirror the images.
Say that again.
1001101 is the first string. And the second string is,
1001.
yeah, this is a string. And the second
This
string is 1001, substring
first
of
one's not a
that.
palindrome, but okay.
Yeah, the first one is not a
Oh
palindrome,
my
so
God,
these
I
are
fixed
already
that.
two this different. Yeah. Yeah, this is a good exercise, yeah. So that this is not a palindrome. Can you also look at something more simpler? Maybe um something like 0 and 00, let's say. Can both of these end at the same state?
No, because
Yeah,
you can
but
add
if
100. You can add 100. You can add
Yeah,
100
what are you
to
adding
both.
now?
You can add 100 to both, or like 10 to both, whichever.
Yeah, you can add like a 10 to both, and then it doesn't work. Okay, so both of these are different. What about like 0 and 000?
It's
10
like still
works
do
again.
the same thing.
Yeah, 10 works
Yeah.
again.
Can any two from this list ever end at the same state?
No, we can just use the same thing. So wait, we can generalize this.
Yeah.
So
Yeah, adding a 1 and
It's
then repeating the same string.
yeah, exactly. But do we are we done now? So what does this tell us? No two can end at the same state, right?
Yeah.
What does that tell us about the number of states we would need?
Oh yeah,
infinite, infinite.
in fairness.
Exactly. You would need infinitely many states. That's sad. That means that can we have a DFA which recognizes palindromes?
Nope.
Yeah, because we need finite. It's not a deterministic infinite automaton, it's a deterministic finite automata. So no DFA possible. That's quite sad. I thought DFAs were all powerful and could do everything. Okay. Well, this is like quite cool stuff though. Um, so what we just saw, I would maybe want to take a moment to formalize this. It's called the uh, Myhill-Nerode theorem. You guys just came up with it. No spelling issue. Okay. What this theorem basically says, I won't write it out, but it says that you can uh you can separate your language into these equivalence classes. And if you don't know what this means, ignore it. You don't have to know. But basically, if you can partition, you can always just partition the language into equivalence classes such that two strings in are equivalent if and only if uh every like for any string you append, so A is equivalent to B, and only if for any S, AS and BS act the same way, both accepted or both rejected. So that's what you're saying. So that they say that any language you can partition into equivalence classes like these, and you can create a DFA so that every equivalence class and every state bijection and you would need at least as many states as the number of equivalence classes. This is
Yeah,
basically what
so
we saw, right?
here we had
Yeah.
infinite equivalence classes, so it didn't work.
Exactly. Here you needed at least infinitely many, so you can't have anything.
But wait, does there exist a construction for precisely equal? Like, did like the theorem give a construction for like when the number of equivalence classes equal to the number of states?
Yeah, then that's a great question. So now you can try to think about when you have finitely many equivalence classes, how can you construct a DFA so that precisely equal number of states are there? I think it's either equal or like plus one of those, but I think that's fine.
Yeah,
Plus or
like
minus one, I
here.
would guess. Yeah. Like here you had four equivalence classes, zero ending with start zero and put one starts zero and zero starts one and zero starts one and one. Yeah. Okay. All right. So that's what the theorem states, and it's actually very powerful in terms of not only does it tell us how what's the minimum number of states needed, but it also gives us a tool or a way to show that okay, you cannot possibly have a DFA recognizing this at all. But anyways, okay, this we're done with. Any questions, comments about anything so far? Okay, okay. So now can we have something more powerful, right? Like DFAs are like kind of not that useful. I would not want to use the word useless. But okay, first of all, okay, before we move on, there's actually a lot of cool stuff you can do just with DFS as well. Like precisely characterize the set of all languages that you can recognize. Like you can, so these languages, they have a name. They're called regular languages. A language is regular if there's a DFA accepting it. And that's a very cool way to characterize all these languages. So let's not do that in class. You can think about it offline and we can take it up later as well. So that's very cool. So that's one question to think about. What are some other questions that come from here? So one thing I already said earlier is okay, of course, how can we make this more powerful so that it does recognize palindromes or it does recognize things that it wasn't earlier, right? Uh, without, let's say, like infinite states is still scuffed. That would mean you would want like a lot of infinite power. You want to ideally keep it like realistic. You want to be able to simulate it with say circuits and stuff, right? Okay, that's some questions that I am thinking of. If you guys have any other interesting questions, I think you can say that and we can try to think about them as well. Okay. Uh, right. So can we have something more powerful? So we had DFAs. Now I'll say, okay, what if we have something? I'm just loud thinking here. What if you have some start state, and maybe you have some bunch of things. Let's say I take away this power of determinism. I say, okay, you don't have to be deterministic. That's fine. So we'll only look at non-deterministic finite automata. What does that mean? It means you don't I won't force you to tell me at every point where to go. I'm going to be more lenient in the sense that let's say you can only just have like a zero from here. There is no one. Or you could also have two zeros leading to two different states. That's also fine. I'm quite lenient about these things now. And
So it's about
I'll also
probability,
no,
grand.
I don't want to involve any probability, so I'll explain. So, how do you know what to accept and what to reject? So, I'll say that out of all these paths, there are multiple paths you can take for every string now, right? Earlier it was deterministic, meaning you knew at every step what path you wanted to take. Over here, there's multiple paths you can take. So now here I say that okay, you accept something if there is some path which accepts, which leads to an accepting state. If all lead to rejecting states, you reject. But if there is some path which leads to accepting state, you accept. Does that make sense?
It's something similar to what Nishant said, combining multiple DFAs and stuff.
Hmm. Yeah. Yeah, I guess that's maybe what I had on my mind. So, um, does it make sense? So what I'm saying, and I'll make it even more like weird. I'm going to say I'm going to add like epsilon transitions. What does that mean? Epsilon is basically like a non-existent word. So if I've read a zero, and then I can just choose to randomly jump to this state for no reason at all. So epsilon means you can choose to randomly do things without anything. Like epsilon basically means the empty string. So I'm going to add epsilon transitions. I'm going to allow multiple zeros. I'm going to allow no zeros also. I'm going to allow this one, maybe something,
Wait, then from
something,
the
something.
initial state, I can
I'm,
just say
hmm.
epsilon going to like the palindrome and then something else randomly going to that thing. So like I can randomly jump to palindrome and I win like every time. It's a palindrome.
Okay, what do you mean? Explain.
So like the initial state is like the
Yeah.
whatever the input. And
Hmm.
then I have this epsilon jump which goes to the final state palindrome. And then I have some other random jump which is say zero, which goes some zero or something which goes to not like 0 and 1 goes to non-palindrome. Both goes to non-palindrome.
Okay,
So
this is
like
your NFA?
yeah, so like by your logic, like I can randomly jump to palindrome. So for any string, technically I have any palindrome, I have done it.
Have you though? Have you really cooked here? What does it mean? I think this is like very cool stuff, by the way. I think it's great that you're thinking in this direction. But except I don't think you're quite there yet. What do I mean? So when do I accept a string? When there exists some path that leads to a final state. So even if one path out of all the many paths leads to a final state, I'm going to accept. So over here, I'm going to accept any string because if you have anything, let's say 0 1 1 0 1 1 0, I'm going to accept this as well because I'll just say do epsilon, go to B and stay at B. Like don't do anything.
Okay,
Every
yeah.
time you read something,
But
just
this is
stay
a
at B.
palindrome, so like it's yeah, for non-palindrome also this will
Oh
work.
my God, yeah. I just yeah.
For non-palindrome will work, yes, I get it.
Yeah.
Um,
So you don't want that to happen. But that's like a great idea though. That's a great idea. So now can we try to cook up something? So first of all, it makes sense that this is like we've relaxed so many conditions. Like surely this is more powerful, right? Maybe it's still not all powerful, but it does feel like it should be nicer than the DFA that we had earlier, right? Hmm. So do you guys want some time to think about how we could create? First of all, do you have any questions about how an NFA works or how it's made or anything like that?
Wait, a DFA cannot have infinite states, but a DFA to count length of a string can. Like there exists a DFA to count the length of a string, right?
What do you mean? Like you need to phrase your problem as a decision problem. So how are you phrasing your problem?
Find the length of the string. Like what is? How do
No,
I?
but that's not a problem, right? Like a problem you wanted to have some set which you're going to accept, and then you want to ask whether it belongs to this accepting, like whether it belongs to this set or not.
A fixed length you can obviously find. Yeah. Uh,
Hmm.
Wait, how are we going to find it for length? Like,
But say the question again.
he says for length it works. I don't get how for length it works. I don't know if we can even get the length of this thing.
Hmm. So I think what Nishant is asking is let's say your DFA should only accept strings of length 5. Can you make a DFA which only accepts strings of length 5?
Oh, yes, I guess we can.
In fact, something more to think about is, can you always create a DFA? If I give you some finite language or some finite set, can you always have a DFA accepting just that finite set?
Can you repeat?
Yeah, the question is, if I give you some finite set of strings, can you always make a DFA that accepts that set and rejects everything else?
Like palindrome didn't work.
But
Oh,
palindrome was an
partition.
Palindrome
infinite
is
set,
infinite
right?
set. Wait, yeah, I think finite should be doable. You create a tree, and then if anything exceeds the length of the tree, we know it's like outside a finite set. So we just go back to some random
Yeah, it
unfinished.
was similar to like how we calculate the
Like
length.
you can
and
just go around itself, yes.
That's a good enough intuition, I think. But yeah, you should think more. And what if like there is some language that you can accept? Then what if you consider the complement of that language? Can you still make some DFA which accepts only the complement of that language and rejects everything else? What do I mean by a complement? I mean like precisely the strings which are not in that set.
No,
That's
but
one
that
question.
complement
Yeah.
might be infinite.
That's fine. That's fine. Maybe both the sets are infinite. If you have a DFA accepting one, can you somehow from this cook another DFA that accepts the complement? I'm thinking of, I'm just loud thinking of a lot of questions here. You can choose whichever question seems interesting enough and work on it to think about it. For example, let's say there are two DFAs recognizing, let's say, two languages. Can you have a DFA that recognizes precisely the intersection of these two languages? Like only accept if it belongs to both these and reject otherwise. What about the union? Like, can you have a DFA that accepts only if it belongs to at least one of them? Mm, these are just some questions. What about concatenation? Like, for example, what I mean is, let's say you have some language L, some set L1, some set L2, and I'm going to define like L1 concatenate L2 as the set of all strings. Basically, you take A and then you add a B at the end, where A comes from L1 and B comes from L2. So if L1 and L2, there are DFAs for L1 and L2, can you cook up a DFA for L1 dot L2? Just some, just I'm just loud thinking the questions that come to my mind. I don't know if these are interesting enough. We can take them up during the week and discuss them. But yeah. Anyways, coming back to NFAs. So what can we do? NFAs seem fairly powerful, yeah? So
Yeah, for NFAs, we can do all that stuff you mentioned, I guess, like intersection and union. Because we can just mention at the end state, we can just do epsilon and it goes there.
yeah, that will work for union, right? Um,
Should know.
yeah. So these things, NFAs, it seems there's some direct ways to do it.
With palindrome, I don't think it's still possible using NFA.
It seems palindrome is still not possible using an NFA. That's quite sad. What is something that's like hard to do in the DFA but you can do in an NFA? NFA. Do you guys want to think about this question or should
Multiple
I spoil
cases,
it for you?
kind of.
Yeah, sorry.
We can check multiple cases in this case. Earlier we had this one.
Huh. So, so
Multiple
can you
cases.
guys, it's not too hard. Can you come up with an example where you cannot cook a DFA but there is like an NFA for it? I mean, surely these NFAs are like so much more powerful. Like it shouldn't be too hard, I think. Do you guys want to think about it for some time? Do you guys want me to spoil it?
We'll think about it.
Do you want to do it in class or do you want to take your time later.
Last 2 minutes.
2 minutes, okay.
Are two languages the same if they have like the same set of alphabets?
By alphabet, I mean like the characters that you're using to make the strings.
Yeah,
So
so
you
they
could
are
have two different languages made from zeros and ones, right? Like so far you've seen like 3, 4 already.
wait, we have different languages for zeros and how?
Yeah, like for example, the set of paradoxes, sorry, not paradox, palindromes. The set of palindromes is not the same as the set of
Oh, it's like, okay, this consonant. Okay, yes, this consonant.
yeah. Okay, I think that's 2 minutes up. I think you guys give it a good try. I'm sorry, I was just messing with you. It turns out that NFAs are like just as powerful as DFAs. Basically, anything you can do with an NFA, you can do with a DFA, and anything you can do with a DFA, you can do with an NFA. Um, that's
What
actually not,
about that freedom?
yeah?
What about that freedom we got in choosing determinants and non-determinants?
Yeah, it was all scam. I just like made you believe that it was actually more powerful, but it's actually really not. It's all just the same, guys. Sorry, I lied. Did
But
I
does
actually ever?
NFAs like
Yeah.
actually do exist?
Huh? What do you mean?
Like NFAs actually exist. Why have we made it NFAs then?
Yeah, why
Can
have we made NFA? Like, what's the point of NFAs? That's like a fair question. So I guess like when people came up with it, maybe they thought NFAs would be more powerful because they do seem more powerful. But then as they explored them, they realized, okay, they're literally just the same as DFAs. It's not adding on to anything. So maybe that's what happened. But actually, it's quite cool because so now the question arises: you still need something more powerful for to simulate your mechanical procedure, right? So, so this proof is not too hard. I will not discuss this in class. You can think about it. And if you need a hint or you need help with something, you can also discuss it amongst yourselves later. And if you need some hint or something, then feel free to DM me. Although I'm not too active on Discord anymore, but I'll try to be more active to talk to you guys if you're interested. Okay, it's not hard. Left as a homework to the student. Okay. So now the question is unanswered, like we need something more powerful. And then that powerful thing that we generalize this to sort of is called a Turing machine. And it's by far the most if we like don't consider stuff like quantum and stuff, then this is like the most powerful model of computation that you can have. And of course, this was, yes, by Alan Turing, and this was originally devised by Alan Turing to help with cracking the Enigma in the World War, but it also ended up solving Hilbert's. How do we pronounce that again? We don't have a Shreya to pronounce it, but this problem. So yeah, so the Turing machine is like the most powerful, and in fact, as it turns out, okay, one of the most like leading problems today is, so even in like DFAs and NFAs, when, so now the question arises, can, okay, first of all, let's go. The question arises, can Turing machines do everything? First of all, okay, first, I also have not told you what a Turing machine is. So a Turing machine is still just a bunch of states, some transition functions, and you also are given a tape where you can write numbers, and every time you can either choose to stay there and access what you have written here, or you can choose to go to the right, or you can choose to go to the left a bunch of times. So basically that's like storing. So earlier we were not able to keep track of what the first number was, and we didn't have any memory of any sort. So what the Turing machine introduced is this memory concept, so that you can store these things that you have seen and then verify them later as to whether they were equal or whatever you want to do. So that's like the intuitive idea. We don't have much time to go into too much details, but I think we've set up enough background that even if you look up on the Wikipedia page, you should be able to follow what a Turing machine is. Um, yeah, so that's that. And then in fact, Turing in his paper ended up, okay, I'm going to give more spoilers, but it's like very cool stuff. So Turing ended up showing that there exists some problem which you can never solve using a Turing machine at all. And that problem is called the um halting problem. Have you heard of this before? There's also very cool stuff. I unfortunately have, I'm very tight on time today, so I was also hoping to talk about this, but this is also something that you can try to think about yourself. So what Turing said was, consider this question: if I give you the description of a Turing machine and an input, can you create a Turing machine, like as input you're going to get a Turing machine and some input, let's say S. So can you create a second Turing machine, let's call it M, which tells you whether on input S whether T is going to halt or not? Meaning, is T going to run forever on input S, or is it going to halt or not? And then Turing showed that you cannot have a machine like this. So basically showed that this problem of whether a Turing machine halts or not is basically you cannot be solved using a Turing machine. So you cannot, there's no mechanical, you cannot have a mechanical procedure for everything. There are possibly some things which you cannot have a mechanical procedure for. This proof is also very understandable. There's like multiple ways which is essentially the same thing. One is by a diagonalization argument, which is quite neat. Then the one is just like a simple proof by contradiction as well. So there's not much prerequisites required for any of this.
Like in the lieu
So
of proving the problem true, he proved the problem false.
I don't know if Turing wanted, like Turing initially thought that the problem was true. But yeah, I don't know. I've read it that Hilbert believed that it was true, and there were a bunch of people who believed that it was true. But I'm not sure if Turing himself believed that it was true before he started out with all of this. In fact, on similar lines, there's some very cool stuff where you can do. Like this Gödel proved later. This is also one of Hilbert's problems, by the way, where he said, in an axiomatic system, can you basically show that if something is true, you should be able to prove it, right? Obviously, if something is true, it's true because you can prove it. But there's some very cool stuff called Gödel's incompleteness theorem, where Gödel showed that in any formal, complete axiomatic and consistent axiomatic system, there exist some true statements which you can never prove. That's also quite cool. It is on like similar lines. Although this comes under like a very cool area called the theory of computation. I really enjoy doing this. One last comment I'll do before I have to go is this non-determinism, right? Like why even introduce non-determinism? So now we have the Turing machines. Okay, some things, some weird things you can't solve with Turing machines, like okay, if there's something hot or not. But you can do most things very neatly in Turing machines and finite time, by the way. What I mean by that. And then mathematicians and computer scientists started asking, okay, can we do it in lesser amount of time with lesser and lesser states, lesser and lesser memory and stuff. So there's this notion of polynomial time, so basically the idea is that if you can do it like fast enough. So if the input is, let's say, if you're taking the input in n bits and you can run the algorithm in, let's say, like n squared or n cube number of steps, then that's fine. That's fine. But if you have something like 2 to the n steps, then that's bad. So now the question arises, okay, now we sort of know like some things we can do, some things we cannot do, but within the things that we can do, how can we optimize them further and reduce the number of time? So that's one thing. So if you've, in fact, I'm sure you might have heard, maybe you've heard of this problem. Basically, if you solve this problem, you're going to get $1 million. It's one of the $1 million problems by Clay Mathematical Institute called P versus NP. All it is asking is whether everything you can do on a deterministic Turing machine. P is basically the set of all languages that you can recognize on a deterministic Turing machine in in polynomial time. And NP is non-deterministic polynomial time, meaning everything that you can recognize on a non-deterministic Turing machine in polynomial time. So now this $1 million question asks whether these two sets are equal or not. So whether you can whether everything you can do on a non-deterministic Turing machine, can you do it on a deterministic Turing machine? But like your time should not blow up. That's the question. But anyway, so that was most of what I wanted to say. Okay. Are there any questions or comments or anything? So just to summarize, we started off with this weirdly named problem, which probably does have a meaning in German. Then we started defining a mechanical procedure. Then we started off with something simple, and then we saw that okay, it has limitations. So we thought that let's make something more powerful, and then it turned out to be scam. It was just as powerful, and then like this sort of last 10 minutes we discussed the Turing machine halting problem and P versus NP stuff like that. This is very cool. If you want to learn more about this, the thing you should look out for is theory of computation. This is what it's called. There's a very nice book by Michael Sipser, so if you're interested, you can look up that book. Okay. If there's no more questions, comments, then I think we'll take a stop. I hope you enjoyed the class as much as I did. And I'll see you guys soon. Thank you. Bye.
Thanks for teaching.
Thank you. Very nice class.
Nice
Bye.
class.
Thank
Bye.
you. Bye.